Section 13.4, differentials. Okay, so what is a differential? Well, in a single dimension, when we have, y is equal to a function of x, our differential is dy equal to f of x, or f prime of x, dx, right? So that's our differential, and we're going to expand on this and take it into functions of two variables. And let's just to remind ourselves, when we talk about an increment, we're talking about delta y and delta x, right? So the differential is taking us to that instantaneous bit of change, whereas the increment is whenever we would do something like a Riemann sum, and we would have some width delta x, right? So some change in x. Okay, so the increment of z is delta z, and that is equal to f of x plus delta x, comma, y plus delta y, minus f of x, y. Okay, so we've moved in z to the point f of x plus delta x, y plus delta y, and then we're going to subtract f of x, y. So this is just, that change in z. All right, so now let's talk about the differential. And it's actually called the total differential. dz. Okay, so the total differential dz is given by the following. If z is a function of x and y, and delta x and delta y are increments of x and y, then the differentials of the independent variables x and y are dx equal to delta x and dy equal to delta y, and the total differential dz is equal to the partial derivative with respect to x, partial derivative of z with respect to x, dx, plus the partial derivative of z with respect to y of dy. Okay, so in other words, dz is equal to fx of xy dx plus fy of xy dy. Okay, so this is called the total differential because it's taking into account both the change in the x direction and in the y direction. So it's accounting for the entire change. All right, so let's do a quick example here. Let's find the total differential, dz, for z equal to 2x sine of y minus 3x squared y squared. All right, so we are first going to have to find the partial derivative with respect to x and then the partial derivative with respect to y. So my partial here is going to be 2 sine y minus 6xy squared. That's the partial with respect to x. And the partial with respect to y is going to be 2x cosine of y minus 6x squared y. So then our total differential is equal to 2 sine y minus 6xy squared dx plus 2x cosine y minus 6x squared y dy. Okay, so that's the total differentiable. Now, just like when we were working with functions in one variable, we would say the function is differentiable. We have that same idea here. So we have differentiability of a function in two variables. So let's go ahead and write that down. Differentiability. So f of xy is differentiable at the point x naught, y naught, if delta z can be written in the form delta z equal to f sub x of x naught, y naught, delta x, plus f sub y, x naught, y naught, delta y, plus some small multiple of the change in x, epsilon 1, delta x, plus some small multiple of the change in y, epsilon 2, delta y, where both epsilon 1 and epsilon 2 are going to go to 0, where both epsilon 1 and epsilon 2 go to 0 as delta x, delta y, delta y go to 0, 0. All right, and we say the function is differentiable over a region R if it's differentiable at each point in R. So f is differentiable in a region R if it is differentiable at every point in that region. All right, so f is differentiable in a region R if it is differentiable at every point in R. Okay, so let's do an example where we show something is differentiable. It is differentiable. Okay, so we begin by finding delta z. So we're looking for the increment of z. So that's going to be equal to, all right, so we have f of x plus delta x, y plus delta y, minus f of x, y. All right, so we can sub in the values here for x and y into our function. So this is equal to, let's see, x plus delta x quantity squared plus 3 times the y value here is y plus delta y, minus f of xy, which is just x squared plus 3y, so distribute the negative, and we get this. All right, so that's equal to x squared plus 2 delta x, well, let's say 2x delta x, plus delta x squared plus 3y plus 3 delta y minus x squared minus 3y. So combining like terms, we are going to get 2x delta x plus delta x squared plus 3 delta y. Okay, and remember we are trying to get this in the form of the partial of f with respect to x times delta x plus the partial of y with respect to y times delta y plus some constant times delta x plus some constant times delta y, just going back to our definition of differentiability. All right, well, if we go back to our function, our partial with respect to x is equal to 2x, and our partial with respect to y is equal to 3. So we want to have this written as 2x times delta x plus 3 times delta y, there we go, 3 times delta y, plus something times delta x plus something times delta y. Well, we come up here and take a look. We have delta x times delta x. That's delta x squared. So that's going to be delta x, and we don't have another delta y, so that'll be 0 times delta y. All right, so this will work. So we have epsilon 1 equal to delta x and epsilon 2 equal to delta y, and that will work so long as epsilon 1, epsilon 2 both go to 0 as delta x, delta y go to 0. So they certainly do. So as delta x, delta y goes to 0, 0, of course, epsilon 1, which is equal to delta x, goes to 0, and delta y, oh, I said E2 is delta y. It's not. Epsilon 2 is not delta y. Epsilon 2 is the 0 here. So let me correct that right now. So that's 0. There we go. And then epsilon 2 is already 0, of course, is going to go to 0 no matter what, because it's already 0. So we have this in the form, go back to white, we have this in the form fx delta x plus fy delta y plus epsilon 1 delta x plus epsilon 2 delta y. Okay, where epsilon 1 and epsilon 2 are defined as delta x and 0. So it follows then from the definition that this is differentiable. So therefore, f of xy is differentiable. Okay, now the good news is we don't have to show that every single time we want to say something is differentiable. So here we go. Sufficient condition for differentiability. This is a theorem. Sufficient condition for, that's illegible. Sufficient condition for differentiability. Okay. Basically, if f is a function of x and y, okay, where f sub x and f sub y are continuous in an open region, open region R, then f is differentiable on R. Okay, so if we have a situation where we have f sub x and f sub y, if those are continuous functions on our region, then f is differentiable on our region. So we do not have to go through the definition of differentiability every single time we want to differentiate something. All right, so what are differentiables good for? Differentials, they're good for making approximations. Okay, so approximations by differentials. Okay, so the idea here is that if we choose points that are close enough together, the epsilon 1 delta x and epsilon 2 delta x kind of, they're so tiny they don't even matter anymore, right? So we can use that as an approximation if we are close enough. So let me write that down. So if x plus delta x, y plus delta y is close enough to the point xy, then epsilon 1 delta x and epsilon 2 delta y become insignificant, right? They're so tiny they don't even matter. And so the result of that is then that the incremental change in z is approximately equal to the differential. So we get delta z is approximately equal to the differential, the total differential dz. Okay, so let's go ahead and do an example where we're going to use that differential to make an approximation. Okay, so let dz approximate the change in z equal to the square root of 4 minus x squared minus y squared as xy moves from the point 1, 1 to the point 1.01, comma 0.97. Okay. All right, so you can tell these are small changes, right? They are small changes from x naught to x1, if you will, from 1 to 1.01 and from 1 to 0.97. So let's go ahead and find dz. So dz is going to be equal to the partial of x, the partial of z with respect to x times delta x plus the partial with respect to y times delta y. So partial x, partial of z with respect to x, delta x, plus the partial of z with respect to y, delta y, not dy, delta y. Okay, so this is going to be equal to, let's see here, so that's going to be 1/2 times 4 minus x squared minus y squared to the negative 1/2 times negative 2x. delta x plus, okay, 1/2 times 4 minus x squared minus y squared to the negative 1/2 times negative 2y delta y. Okay, so that will simplify a little bit. We do get some nice cancellation there, so we end up with negative delta x over the square root of 4 minus x squared minus y squared minus, ooh, I dropped my x here. This should be minus x delta x, there we go, minus y delta y over the square root of 4 minus x squared minus y squared. So now what we have to do is plug in the values for x and y and for delta x and delta y. So the question is, what's x and y? I've got 2 points here, right? Which one's xy? Well, this is the point xy. This is x plus delta x, and this is y plus delta y. Okay, so this original point is our x and y value, and then our delta x and our delta y are just going to be the difference. So I'm going to grab another color just so that it's different. So we have delta x is equal to 1.01 minus 1, which is 0.01. We have delta y is equal to 0.97 minus 1, which is negative 0.03. Okay, so we're going to plug in our point, 1, 1, and our incremental changes for x and y. So this becomes negative 1 times 0.01 divided by the square root of 4 minus 1 squared minus 1 squared minus y is 1 times negative 0.03 divided by the square root of 4 minus 1 minus 1. So that's equal to negative 0.01 plus 0.03 divided by the square root of 2. So that's going to be 0.02 divided by root 2, which is approximately 0.0141. So our change in z here is approximately 0.0141. Now, how does that stack up to the actual change in z? Well, let's check it out. So delta z is equal to f of 1.01, 0.97 minus f of 1, So we plug these values in. This becomes the square root of 4 minus 1.01 squared minus 0.97 squared minus the square root of 4 minus 1 squared minus 1 squared. So this is equal to the square root of 2.039 minus root 2. So that is approximately 0.1372. I dropped a 0. Let's fix that. 0.01372. There we go. So that's here. So it's really quite close, right? It's within 1,000th of each other, less than 1,000th really. So it's really not a bad approximation when we are doing very, very small changes. Now, by the very nature of approximations, we have an error, right? So of course we have to think about the error and how the error comes into play. So with any approximation, there's going to be an error, right? Because it's by its very nature an approximation, meaning it's not 100% accurate. So there is going to be an error. And depending on how many times we introduce that error into our setup, into the problem that we're working, that error can propagate and it can grow very large very quickly if we're not careful. So we need to be aware of the fact that with any approximation, there is an error. So let's see an example where we have an error that's going to be propagated by finding volume. Okay, so with any approximation, there's going to be error just by its the very nature of an approximation. So let's do an example where we see how the error, which can be very small, can be propagated to become to have a much bigger impact, okay, because we're using it over several dimensions. So here we go, example. All right, so in this example, we have a box. So we have a rectangular box. And we've measured it so that our dimensions are x equal to 50 centimeters, y equal to 20 centimeters, and z equal to 15 centimeters. The problem is with our measurements, we have a plus or minus 0.1 millimeter margin of error. Okay, so our job then is going to be able to find that propagated error using dV. So we're going to use dV to find the propagated error. Okay, now according to the dimensions we're given, our measured volume is length times width times height, or 50 times 20 times 15, which comes out to be 15,000 cubic centimeters. Okay, so that's our measured volume. So now let's go through and let's use dV to find the propagated error. So V is equal to XYZ. So dV is going to be equal to the partial of V with respect to X dx plus the partial of V with respect to Y dy plus the partial of V with respect to Z dz. Okay, so that's going to be yz dx plus xz dy plus xy dz. Okay, so dx, dy, and dz is the possible change that we have, the plus or minus 1 millimeter, 0.1 millimeter. Oh, and by the way, since all of our dimensions are in centimeters, we should make a note that 0.1 millimeters is 0.01 centimeters. So that'll be our differential here for dx, dy, and dz. So we have y and z. So those are 20 times 15 times plus or minus 0.01. And all of these are centimeters. So this is going to come out as centimeters cubed. Plus x was 50, z was 15 times plus or minus 0.01 plus 50 times 20 times 0.01. Alrighty, so that's all going to come out to 20 times 15, which is 300, plus 50 times 15, which is, what is that? 15, 20, 75, 750, plus 50 times 20, which would be 1,000, times plus or minus 0.01. So that's going to be 2,050 times plus or minus 0.01, which is equal to plus or minus 20.5 cubic centimeters. Okay, so our propagated error is 20.5 cubic centimeters, give or take, right? So our measured volume was 15,000 cubic centimeters. So that's going to be off by possibly 20.5 cubic centimeters, either too high or too low by that amount. Okay. All right. Now we might be asked to find the relative error. So let me write this down. The relative error. This is going to be dV divided by V. So the differential of the volume divided by the volume that we measured. So this is going to be plus or minus 20.5 divided by 15,000. And if we pop that in our calculator, we get that that is equal to plus or minus 0.0014, which relative error we usually would put as a percentage. So that's going to be 0.14%. Give or take, plus or minus, okay? So that's a percent error of about 0.14%. Okay, so one more theorem in this section. Differentiability implies continuity at a point. Does not necessarily go the other direction, just like in two dimensions. You know, if we have a cusp or something, it's not differentiable there, even though it's continuous. Same idea. This does not go in the opposite direction, but differentiability does imply continuity. So if a function, f of xy, is differentiable at the point x naught, y naught, then it is continuous at x naught, y naught. So if we know something is differentiable, we know it's continuous at those points. All right, so that's the last thought for this section. As always, if you have questions, please let me know.